to make sure everyone can see it.
Looks good.
Yep. All right. Okay. So so this is joint work with sort of a current student, Valentine. It's like a former student, Jeremy Schmidt, and a collaborator, Jin Zhang, who's a professor of psychology at the University of Michigan. Aspects of it has been generously funded by the National Science Foundation. It's like, and then more recently by the Air Force. So, so let me sort of give you a little bit of motivation for why I'm interested in this connection between sort of information geometry and second mechanics. And from my perspective, I'm interested in this issue of the unification of information and mechanical systems. So in particular, say you have a system with information and physical layers, and typically it's when one tries to address the issue of uncertainty, it's like in a, say, a network of drones, there's a tendency to treat this information processing layer, it's like in discrete time, and the physical dynamics in continuous time, okay? And in particular, it's like you tend to assume, if you will, that the you can close the control loop, it's like for the physical dynamics, and then the question of how do you go about, for example, exploring it's like the environment in a way which allows you to extract information as efficiently as possible, is then sort of superimposed on that as a separate optimization layer. So as a consequence of this, it's like these hybrid systems are typically sequentially optimized as opposed to concurrently optimized. This reflects an assumption, if you will, that there is a separation of timescales between how fast the information changes versus how fast the physical dynamics changes. So more or less, it's like the assumption is that the environment which you're trying to extract information from is not changing as rapidly as the underlying dynamics, if you will. So what we're going to try to do then is that we're going to try to relate information geometry and discrete mechanics. And there's a approach in numerical analysis known as backward error analysis. And the basic idea behind backward error analysis is that in contrast to the usual error analysis approach where you ask the question, it's like if you have a continuous dynamical system and you have a numerical discretization, to what extent the numerical discretization approximates the continuous dynamics? What you instead ask is, if you give me a numerical method, what is in some sense the closest continuous dynamical system to that? So anyway, with this paradigm of backward error analysis, it's like what we hope to do is to think of various machine learning algorithms as the exact time H flow of a continuous dynamical system, but in the space of probability distributions. And the motivation for doing this then is that one would be able to combine it's like the information learning layers it's like together with the mechanical control aspects, and give you sort of a unified treatment of information mechanical systems. And to be sort of more precise about the motivations we have in mind, what we're really sort of looking at are these little drones. It's like, and then instead of just having a small number of them, you have potentially swarms of them. And drones, of course, have been used. It's like to perform reconnaissance. It's like out in the field. But I think where it's perhaps more interesting from the point of view of the separation of timescales issue is if you try to use them to perform reconnaissance inside buildings in sort of built-up urban areas. And so if you're trying to fly these things indoors, then one of the real challenges is that these drones, especially the small ones, are very easy to disable by just throwing blankets at them. So in order to avoid this, they have to fly really, really fast, typically about 10 meters per second or about 22 miles per hour. And so basically what happens is that these things are zipping down. It's like a corridor. It's like they fly past an open door, and then suddenly it's like there's a whole bunch of information which is available to them, which was prior to that obscured. So there's a sense in which the information landscape, or at least the accessible part of the information landscape, is really changing now at a time scale which is comparable to the dynamics. And so there is no longer a separation of timescales, which allows you to separate the the control of the mechanical system. It's like from the information optimization part. Okay, so the basic idea then is that this whole idea of information gathering and coordination of swarms of drones could potentially benefit from sort of a more unified treatment of both the learning aspects as well as mechanical aspects. So either thinking both of them in discrete time or both of them in continuous time. Okay, so it's like, so I'm preaching to the choir here. It's like, so this is sort of a brief about information geometry. So the basic idea, of course, is that you use differential geometric tools to describe, say, manifolds or probability density functions. And I guess it's like it's most well developed. It's like when for certain classes, parametric families of probability densities, which you can then embed. It's like in some way into the ambient space of all probability distributions to the same support, and you can think of the coordinates. It's like on this manifold. It's, I guess, corresponding to, say, the parametric values of these parametric families. And of course, what you like to do is that instead of looking at the kind of geometry which is induced, it's like on the space of parameters, you want to instead study these problems using the intrinsic properties of these parametric families. It's like embedded, it's like in the space of probability densities. Okay, and of course this leads to geometric concepts like the Riemannian metric, affine connections, and curvature. And these, of course, in turn are related to statistical issues like asymptotic efficiency of maximum likelihood estimators. The way I like to think about certain classes of machine learning algorithms then is to think of them as optimization problems, where you're thinking of trying to find then some probability distribution in some parametric family. It's like which minimizes the mismatch with the data. And of course, it's like one very natural way to measure that mismatch in the data is to use these divergence or contrast functions, which are, of course, asymmetric analogs of distance functions, and they provide a unified way of measuring information, energy, and entropy. So you probably know already that these divergence functions deduce metrics and connections on the information manifold, and then these differential geometric structures yield more natural optimization algorithms in the sense of optimization of manifolds than working in the parametric representation.
Can I just ask a quick question?
Sure.
When you say we probably know this, yeah, we do. But how often do you get to say that in this talk?
How often do we get to say that?
How many audiences do you talk to that know all this stuff?
Well, I mean, I wouldn't say that it's like to most audiences, right?
Okay, yeah. I just was wondering.
So, right, yeah.
We think that there are not that many information geometry seminars around.
Sure, that's right. Yeah, so this is an unusual audience. I mean, this talk was, of course, and you'll see it's like that. It's like the first part of this is meant to be a quick introduction to information geometry in the subsequent slides. But in a sense, this is sort of a problem I have. It's like irrespective of what audience I talk to, because there's always some subset of what I do which is not known to the audience. But it's like, but of course this audience knows a whole lot about information geometry, so I'm just skimming this. So let me say a little bit more about the other things which perhaps are less familiar. It's like one of which is this issue of discrete mechanics. So discrete mechanics then is an attempt to try to construct geometric structure preserving discretizations of analytical mechanical systems, typically described in terms of Lagrangian and Hamiltonian mechanics. And in particular, it's like the kind of discrete mechanics which we do is based on a discrete version of Hamilton's principle, which is a variational principle. So what's interesting, though, is that the divergence function in information geometry then has an interpretation as a discrete Lagrangian, which then is a generating function of a symplectic map. And a consequence of this then is that it allows you to impart a mechanical interpretation to certain machine learning algorithms, and allows such algorithms to be viewed again as time-page flows of continuous mechanical systems. So there's a very good understanding, it's like in the area of discrete mechanics, about how discretizations of mechanics are then related to continuous dynamics. And because the divergence function can be viewed as one of these discrete Lagrangians, which is a fundamental object in discrete mechanics, we hope to leverage that analogy then to say something about, again, thinking about machine learning algorithms as continuous time flows in that sense. Okay, so this is of course a review about divergence functions. It's a map from 2 copies of the information manifold to the non-negative rails, and it's sufficiently differentiable, and it satisfies a bunch of properties which I won't go too much into. And again, divergence functions act as pseudo-distance functions in the sense that they're non-negative, but they don't need to be symmetric. Okay, so so given one of these divergence functions, you can of course compute sort of the a Riemannian metric associated with this, as well as a pair of torsion-free dual connections. And they're dual with respect to the induced metric in the sense that if you have two connections associated with these, associated with these two dual connections are two parallel transports. And so if you take a pair of vectors and you parallel transport each of them, where the first one is parallel transported by one of the connections and the other one is parallel transported by the other connection, then the inner product with respect to the metric, it's like, you know, stays invariant under that parallel transport. Okay, so this is the sense in which they're dual with respect to this induced metric. So, so these dual connections, of course, can be expressed in terms of the Levi-Civita connection, as well as a skewness tensor. Okay, so what's going to happen then is that this skewness tensor is going to show up later in the discussion, because that's sort of the inverse problem, which is that you know, it's like these divergence functions induce metrics, and they induce this pair of affine connections. So the inverse question is, if you have, if you prescribe a pair of affine connections and you prescribe a metric, can you then construct a divergence function which induces those things? And we'll see how that happens later on. Okay. So anyway, it's like, so examples of this, of course, are things like the Bregman divergence, which come from a choice of a convex function. And if the convex function is, for example, the negative Shannon entropy, then the associated Bregman divergence is the Kullback-Leibler divergence, and the associated Riemannian metric is the Fisher-Rao metric. Okay. All right. So that's, of course, just a quick review. It's like of information geometry. So let me say a little bit in greater depth about discrete mechanics, and in particular, discrete mechanics falls into a larger class of methods known as geometric integrators. So geometric integrators are a class of numerical methods that preserve geometric properties. Examples of these include things like symplecticity, momentum, and you know, the spaces on which they evolve. It's, for example, might have structures, so they could be a Lie group, or they could be homogeneous spaces. And so the question is, how do you systematically construct numerical methods which respect those properties? Okay, and the motivation for doing all of this is that this tends to result in numerical simulations with better long-time numerical stability and better qualitative agreement with the exact flow. So let me maybe sort of expand a little bit on this idea. So if you think about numerical methods and you sort of, you look at this whole issue of backward error analysis, then in practice, you know, the only things which you can reliably extract from long-time numerical simulations are properties of the system which are in some sense structurally stable, which is to say that these are properties of the system which, if you were to perturb the dynamical system slightly, you know, wouldn't change too much. Okay. So you might ask then what value geometric integration plays is like in this, and the value it places is the following: that when you have geometric integrators which preserve geometric properties, then the way to sort of think about it is that, well, okay, the notion of structural stability is respect to a class of perturbations, and if you have a generic method, then those perturbations would be generic, and the set again of things which are structurally stable with respect to generic perturbations which are small, it's like you know, tends to be quite small. But if you have perturbations which preserve certain geometric structures, then they're in some sense constrained. And the hope is that the things which are then structurally stable with respect to these constrained perturbations would be larger. And as a consequence of that, you can extract things more reliably out of these long-term simulations. So that's sort of one you know, way to think about why geometric integrators are potentially useful for at least certain classes of terms. So the way we do this is by looking at a discrete version of so Hamilton's principle. Okay, so Hamilton's principle states that if you have an initial point and a final point, I guess I should have asked whether you can see my cursor.
Yeah, we can.
Okay, all right. So if you have an initial point and a final point, then the curve which connects that those 2 points is that which extremizes the action integral, which is the integral of kinetic minus potential energy. Okay, so this is of course a very nice way of describing mechanics without relying on coordinates, if you will. Okay, so this is sort of a covariant way of describing dynamics. And then the way one might want to discretize this is that instead of having a continuous curve, you imagine then having, say, a bunch of points which sample that curve in some sense. And then instead of writing down the action integral, you replace it with what we call sort of, in retrospect, a poorly worded term. It's like, which we call the discrete Lagrangian, which you should think of as a small piece of the action integral over sort of an adjacent pair of points. So if you have Q0 and Q1 here, you think of a discrete Lagrangian, which approximates the action integral from Q0 to Q1, okay? And to be more precise, it should ideally approximate what is called the exact discrete Lagrangian, which is the action integral evaluated on a particular solution of the all Lagrange equations, which satisfies the boundary conditions, okay? So of course that is not computable, because in order to compute it, you need to be able to solve the all Lagrange equations exactly. But nevertheless, that characterization turns out to be useful in terms of how you go about systematically constructing discretizations. So this thing then is related to Jacobi's solution of the Hamilton-Jacobi equation. What happens then is that if you take this Jacobi solution, then it generates the exact time h flow of the corresponding all Lagrange equations. So I already said that the discrete Lagrangian can be viewed as a small piece of the action integral. So if you sum it all up, you get something which is a good approximation of the action integral over the entire time interval. And then the discrete Hamilton's principle states that the variations of this are 0. It's like for variations which keep the endpoints fixed. So this is in direct analogy to the usual Hamilton's principle, where you say that if you have an initial and a final point, you look at all curves which maintain those boundary conditions, and you vary the curves, and you want the action to be stationary with respect to them. So this is sort of the discrete analog of this. And when you do that, you end up getting what we call the discrete all Lagrange equations. And then here, there's a bit of notation. So this D2 just means I'm taking a derivative with respect to the second slot, which here is QK. And then this D1 is, again, a derivative with respect to the first slot, which again is QK. So, so the derivative for the discrete Lagrangian at sort of 2 previous points, plus the derivative of the discrete Lagrangian with respect to QK of the, the current and the next point is equal to 0. You can interpret this as a sort of a momentum matching condition by introducing what we call the discrete Legendre transforms. So there's a momentum term, it's like, which can be expressed in terms of, again, these partial derivatives of discrete Lagrangian. And you can check that this is equivalent to this. And this particular description, of course, is nothing more than a characterization of a symplectic map in terms of a type 1 generating function, which is this discrete Lagrangian. So you should think of the discrete Lagrangian as a type 1 generating function of a symplectic map. And of course, that is consistent with it being related to Jacobi's solution of the Hamilton-Jacobi equation. Okay, so let me say a little bit about if you have a mechanical system, what are the benefits to constructing a numerical method from this sort of discrete Lagrangian perspective. And the first thing is that you have a discrete version of No-First theorem. So No-First theorem says that if there's a symmetry of problem, then there's an associated conservation law. So something analogous happens here. If you're discrete Lagrangian, it's like, which depends on 2 copies of position. If you take those 2 positions and say you rotate them by the same rotation, and it turns out that the discrete Lagrangian is invariant under this diagonal action of the group on these 2 copies of the configuration space, then there's an associated momentum which is preserved. So again, it's like if you're looking at, say, rigid body dynamics, which in the continuous case is invariant under the rotation group, and then the associated momentum conservation law is angular momentum. The same thing is true in the discrete case. If you construct this discrete Lagrangian in such a way that it respects the original symmetry, then the numerical method, the variational integrator you get from this will again respect that symmetry. Okay. So the other thing it's like, which is nice, is this whole idea of variational error analysis. So if you've ever done error analysis of a numerical method, you know that basically all you really do is that you do Taylor expansions everywhere, and you compare, it's like the Taylor expansion of your numerical method with the exact Taylor flow, and then you sort of match terms term by term, and that allows you to conclude something about the local error which you make, and then from that, via some sort of Grunwald kind of argument, you can say something about the global error. So that's oftentimes very tedious. And so one of the nice things about variational integrators is this thing where instead of analyzing the numerical method directly, you can analyze something about the properties of the discrete Lagrangian. So the discrete Lagrangian, of course, is the scalar value function. And what happens is that if you have this scalar value discrete Lagrangian, and you compare it to this exact discrete Lagrangian, and you can show that, as sort of functions of h, right, it approximates the exact discrete Lagrangian to a certain order of accuracy, then the corresponding variational integrator will have the same order of accuracy. So again, typically it's much easier to establish this kind of error estimate than it is to directly work with the numerical method. In addition to that, it's like we also have, it's like additional theorems or meta theorems which allow you to say that, well, if you construct this method, you construct a discrete Lagrangian using, say, an appropriate choice of function space and an appropriate quadrature rule, then we can relate the order 2 properties of those 2 things. So you don't even have to do this, in a sense, in many examples. So, all right. So there are additional motivations for studying symplectic discretizations, and one of which is that, even if you have differential equations which are not Hamiltonian, a lot of times, especially in engineering and in finance, you're interested in this question of sensitivity, right? So you're interested in asking, well, what happens if there's uncertainty, or if I change things, how does the system solution respond? And this is oftentimes addressed in terms of what are called adjoint equations. So the main point is that if you have a system of differential equations and you add to that system the adjoint system, then the combined system of the differential equations and the adjoint equations have a Hamiltonian structure, even if the original system does not. And in particular, if you don't preserve sort of this geometric property known as symplecticity, then the relationship between the primal and the adjoint variables break down. And in practice, what that means is that you no longer have this relationship where if you take the adjoint and you discretize, that it's equivalent to discretizing and taking the adjoint. Where does this show up? This shows up, obviously, for example, if you're trying to train, it's like a neural network. If you're trying to train a neural network, right, you want to vary the weights, for example. It's like in the neural network in order to minimize the loss function. And so what you really want to do is you want to compute the sensitivity of the loss function with respect to the changes in the weights. But in practice, you want to look at the adjoint relationship because you want to be able to say that, well, if I want to decrease the loss function, how should I change all the weights? Okay, so that's what the adjoint equations do for you. And if that method, if the neural network is, it's like instead of the neural network, you had sort of a discretization, it's like of a system of differential equations, then when you discretize that, it's like you might want to apply the same discretization to the continuous adjoint equations. And if you do that, oftentimes you'll have a property that, the candidate descent direction, it's like which you get, it's like from solving the discrete adjoint equations is actually not it's not actually a descent direction of the discretization. And so your optimization algorithm just fails. Whereas if you use the symplectic discretization, it's like for the combined system, then everything works out the way it should. And it would give you basically the same answer you would have gotten if you had sort of done it the hard way, where you did automatic differentiation applied to the discretization. Okay, so in some sense, what symplectic discretizations buy you, it's like in the case of adjoint systems, is that it allows you to use numerical methods as an alternative to doing automatic differentiation when solving adjoint systems. Okay. Anyway, so there is, so I haven't actually said how you go about constructing one of these discrete Lagrangians, And one way to do this is that there is an alternative characterization of this exact discrete Lagrangian given in the following expression. So what you do is that you look at the action integral and you extremize it over the class of twice differentiable curves subject to the boundary conditions. So it's easy to convince yourself that that's equivalent to the usual characterization of Jacobi's equation, because the stationarity conditions for this are exactly the Lagrange equations. So you can evaluate this extremal by just evaluating the action on something which satisfies the Lagrange equations and the boundary conditions, which is exactly the usual characterization. But this characterization, it's like this variational characterization more naturally lends itself to discretization, because what you can do instead is that you can replace this family as twice differentiable curves with some finite dimensional function space, and you can replace the quadrature rule, the integral, with some numerical quadrature. Okay, all right. And then again, some meta theorems, and one of the meta theorems says that if this function space you've chosen, which oftentimes we think of as being parameterized by maybe the values of the position, it's like at a bunch of times. If it has the property that it transforms in the right way under a symmetry group, then the resulting discrete Lagrangian is going to be group invariant, and then by this discrete Noether theorem, it will satisfy a momentum conservation law. So what do I mean by group equivariant interpolatory functions? So if you think of the curve as being parameterized by a bunch of discrete values, and you say you take all these positions, it's like, and you rotate all of them, and you look at the interpolatory function associated with new data, then the original curve and the new curve should be related by the transformation, by the rotation which related the initial data, right? And you know, it's oftentimes easy to do this in the ODE case. It's harder in the PDE case to do this. But in the ODE case, this is fairly well understood, and it then naturally leads to discretizations which respect momentum conservation. And then the other thing is that, as I sort of alluded to, if you sort of choose good function spaces which exhibit certain best approximation rates, then the numerical method you get from it will also respect that best approximation rate. So what that basically means, in not too many words, is that if I know sort of a priori something about the regularity class the solution lives in, and then I have access to sort of approximation theoretic results which say that, you know, for that particular sort of function space, you know, it's like this family of, you know, it's like finite dimensional function space have a good rate of approximation, then you can use that, it's like to construct a variational integrator, and the variational integrator is guaranteed to have, you know, it's like the error properties you expect, it's like from the best approximation results. So for example, if you have a spectral method, right, then you know, probably know that spectral methods converge really, really fast. They converge sort of geometrically, and it has to do basically with the fact that, you know, it's like if you have a real analytic solution or you have a real analytic function, then, you know, the approximation, it's like by a spectral basis has an error which decays geometrically. So so many numerical methods, it's like can be understood, it's like in terms again of sort of, you know, various best approximation properties of function spaces, and this result more or less shows you that the same kind of idea applies, and this then gives you a way to systematically construct good variational integrators which are adapted to the kind of problems you're interested in. Okay, so that was sort of a long, it's like review, it's like of you know, geometric integrators and in particular variational integrators. So let me try to tie it back then with information geometry. So the first thing is that, so if you look at this exact discrete Lagrangian, okay, you can show basically that, okay, so I should say that, okay, so I want to look at the exact discrete Lagrangian associated with a geodesic flow, and in particular with respect to a geodesic flow which is induced by this metric G, which comes from a given divergence function, okay? So what you can basically show then is that if you take 1 over h times the divergence function, and you compare it to this exact discrete Lagrangian associated geodesic flow, then the error you make, it's like as h goes to 0 is big O of h cubed, okay? So, so you might recall that this is, this looks a little bit like this variational error analysis result we said. And so what it more or less says is that you can think of the divergence function as being a discrete Lagrangian appropriately scaled. Okay, and if you took the divergence function and you treated it as a discrete Lagrangian, and you used the variational integrator to construct a time marching method, then you would have a quadratic approximation of the geodesic flow associated with that metric. Okay, and this is true. It's like if this divergence function is related, for example, to the Bregman divergence, right? So it's always true that this is consistent, but if the divergence is a Bregman divergence, for example, then that consistency is up to second order. It's not just first order accurate. Okay, so this is sort of a result which we showed, and then there's sort of the converse. Well, not really a converse, but there's also, again, it's like this issue of canonical divergences, which is to say that if you have a divergence function which induces a prescribed metric and a pair of dual connections. So if you prescribe the metric and the dual connections, how do you find a divergence function which induces those things? So one way to do this is to look at the Hamilton-Jacobi theory. It's like for the following Lagrangian. So this is, of course, it's like just a kinetic energy term associated with the metric. That's fairly natural. And then this is that skewness, it's like tensor, which we sort of looked at earlier, which again is a measure of the extent to which the sort of the pair of sort of dual connections deviates from the Levi-Civita connection. Okay, so if you contract that, it's like with sort of 3 copies of the velocity, and then you appropriately scale it, you get this Lagrangian, and then you want to construct at least a second order accurate approximation of Jacobi solution. And of course you can do this, it's like by using the kind of approximation techniques which we had developed for variational integrators. Okay, so there is, it at least seems suggestive that there is a natural way in which you can think of divergence functions as being related to objects which are known to be important in discretizing mechanical systems. And then conversely, it's like you can use, it's like some of the tools which have been developed in discrete mechanics to construct, amongst other things, canonical divergences. All right, so right now it's like we've just talked about metrics and geodesic flows. You might ask, well, how do you incorporate measurements and data? So imagine if you want to do some sort of, say, data assimilation. It's like where you have, it's like you're trying to sort of update, it's like a prior with data in a way which minimizes the mismatch between the sort of, the posterior, it's like, with the data. It's like, then one way to do this is from a mechanical perspective. All right, so so if the xi's are the model distributions, it's like which again model your knowledge of the real world distribution you're trying to approximate, and then the yi's are the data generated from this unknown real distribution. And of course you can measure the mismatch, it's like by using the divergence function. And so you can think of that as being like a potential energy in the problem. So if you just had a potential energy and kinetic energy, of course, it's like then, it's like you would have a problem because you would have these arbitrarily large changes, it's like in the estimate. So one thing you can do, of course, to make the estimate change a little bit more gently is to have a kinetic energy term. So the way it's like we've proposed to introduce a kinetic energy term is to have a divergence function between 2 copies of the estimator. Okay, so the divergence function, it's like plays sort of a dual role, both in terms of constructing the potential energy, measuring the mismatch between the estimator, it's like, and the real world in some sense, and then it's like it also has a kinetic-like energy term having to do with the the previous state and the current or the updated state. Okay, so again, the hope is that you can use these backward error analyses tools to relate this to a continuous Lagrangian system, and then to view, a class of variational machine learning algorithms as continuous time dynamical systems. So I should mention that this expression where you sort of are comparing, it's like 2 sequences, using the divergence function, turns out sort of manifests itself also in sort of some work on trying to look at continuous analogs of the Nesterov algorithm. So I'll talk a little bit about that in a little bit. And so there's also sort of this connection, it's like which we're currently exploring between discrete mechanics and accelerated optimization. And so, of course, it's like you can think of machine learning as an optimization, or at least a class of machine learning algorithms as an optimization problem. And then conversely, you can think of optimization problem as a learning type problem, right? So if you have an optimization problem where, say, you want to minimize some function, it's like over, say, some convex domain, then you probably know that Nesterov introduced what he called the accelerated gradient method, which is given in the following way. And if you have step sizes which are sufficiently small, then you can show that the sequence of iterates converge to the global minimizer at a rate which looks like big O of 1 over k squared, where k is the iteration number. Okay, so the reason, of course, why that's interesting is because if you were to use standard gradient descent methods, it only converges at big O of 1 over k. And in addition to that, Nesterov showed that if you look at the class of methods which only use information about the gradients of the function at consecutive iterates, then this rate of 1 over k squared is optimal. Okay, so since then there's been, of course, a lot of interest in trying to understand, well, why does it work? Are there sort of ways to generalize this and things along those lines? So back in 2016, it's like one of the ways it's like people tried to do this is, so there's this paper by Sue Boyd and Candace, which shows that you can think of the Nesterov scheme as being associated in the time t equals to 0 limit or h equals 0 limit of some sort of continuous second order differential equation. And it's like if you rescale, it's like the time appropriately, it's like you can identify the dynamics of the Nesterov algorithm with the dynamics of this differential equation. Okay. All right. So so this is, of course, it's like the Nesterov case where you have this 1 over k squared thing. So one of the other questions is there a way, again, to generalize it so that you have continuous dynamical systems which converge at, say, potentially faster rates, okay? So one way to do this is stuff which is due to Michael Jordan in this paper, so I'll go back to that. So the basic idea is that you can generalize this continuous formulation in the following way. You write down, again, this Bregman divergence. And if these 2 points are close, then this Bregman divergence is very well approximated by this Hessian metric, which is given here. Okay, so so Michael Jordan, it's like in his group, it's like introduced this Bregman Lagrangian and Bregman Hamiltonian, which is given by these expressions. And here you have the divergence function evaluated at 2 nearby points, right? So you should think of that morally, again, as being something like a kinetic energy term, which is consistent with what I talked about earlier about using the divergence function to do something which approximates kinetic energy. And of course, this term is the cost function. It's like what you're trying to minimize, which obviously plays the role of a potential, and then some sort of time-dependent scaling. So by its very nature, it's necessary, of course, for both the Lagrangians and Hamiltonians, it's like to be time-dependent. And the reason, of course, is because if you look at the differential equation, it's like of Sue Boyd and Candace, right? There is essentially a dissipation term which is time-dependent. Okay, so so you probably know that if you have a Lagrangian and Hamiltonian system which is time invariant, then there's an associated energy conservation law. Okay, so it's not possible for a Lagrangian and Hamiltonian formulation that's like to model something which is dissipative if it's not time dependent. So the time dependence in some sense is critical to this. Okay. So anyway, so this, in some sense has a form which is at least, similar to the form which we had. It's in terms of just the discrete Lagrangian expressed in terms of a divergence function applied to pairs of points, and then a divergence function applied to the data. It's like, and the sort of the measurement. So here, of course, it's like you replace that with just the potential function which you're trying to minimize. Okay, all right. So then under suitable group conditions.
Okay, can I ask one question? I was,
yes.
Okay, if you go back to the previous slide, yes.
This one? Yeah.
No, again, previous slide, please. Yes, okay, did you look, okay, for example, if your Hessian matrix is not well conditioned, then, okay, whether it has impact on the convergence rate or not?
Oh, you mean if for example, yeah, if the H is not, I mean, if it's convex, but maybe it's sort of elongated in one direction,
yes.
whether, yeah, I suspect it does. We haven't really sort of looked at that that carefully. But yeah, I mean, it's like I think you're right that there's an art. It's like in choosing how choosing this H function in a way which you know, well conditions the problem, right? So there clearly has to be some sort of conditioning. It's like which comes into play. So I mean, the framework is very general. It's like and you know, there haven't been. I mean, there's a lot of, I guess, tweaking. It's like in tuning, and one has to do. It's like in order to make it practical. Yeah.
There are actually going to be problems where the natural formulations have exponentially ill-conditioned Hessian metrics.
Okay.
It's going to happen all the time in time series.
Right. Okay. Yeah. So.
Yeah, I have a question. So
yes,
do you know, do we have an interpretation for this conservation of energy in terms of information geometry? And this,
well, the energy isn't conserved, right? As because the Lagrangians and Hamiltonians are time dependent, so the energy isn't conserved. You can of course, it's like, you know, do the extended phase space trick. It's like where you sort of add an additional copy of time in some sense,
right.
And then there's a term like E times T. It's like which shows up in the Lagrangian and Hamiltonian, and then there's a modified energy which is conserved with respect to those things. But that then just measures. Then it becomes sort of an energy balance type relationship, right? But I'm not sure what the interpretation in terms of information geometry would be. That's a good question. Yes.
Yeah,
all right.
Thank you.
Let me try to, yeah. So anyway, so the point is that if you sort of choose these alpha, betas, and gammas as a function of time in a nice way, in particular, these are examples of choices you can make, then the all Lagrange flow converges to the optimal value at 1 over t to the p for any p, okay? So now you have this fundamental disconnect, right? Because on the one hand, it's like you have the Nesterov result, which says that the best you can do is 1 over t squared, or the analogous thing is 1 over t squared, right? But you have this continuous flow, which can be sort of converging arbitrarily fast. And so one obvious question is, well, what gives? It's like, and our current working hypothesis is that you can't construct a good enough approximation of this continuous flow without giving up something, perhaps, you know, maybe explicitness, or, you know, it's like requiring you to use more information. It's like about the gradients. But nevertheless, it you know, allows you to construct methods which potentially could converge faster, but maybe at a cost of greater computational effort. So right now, what we're exploring, so I didn't mention this in the slides, this is sort of very recent work. What we've been exploring is using time-adaptive variational integrators to try to discretize these kind of Nesterov, or these kind of, you know, it's like Bregman, Lagrangian, Hamiltonian systems. Okay, so so let me maybe briefly talk about the adaptive methods, right? So, all right, so there you can introduce a you can introduce basically a new time-like parameter, and then which is potentially a rescaling of time. It's like via this monitor function. And when you do that, when you do this sort of time rescaling, you get a new Hamiltonian, which is called the Poincare transformed Hamiltonian, which is given here. And if you look at the sort of the level set, it's like where the energy is 0, then you can identify the dynamics, it's like which goes through this to the original dynamics. So maybe that's somehow related. It's like to your question, it's like about, you know, energy conservation. It's like being related to information geometry, but we'll have to think a little bit more about that. So in any case, the bottom line is that, you know, via this Poincare transformation, it's like you can construct, you know, symplectic integrators, which allow you to take arbitrarily, well, it allows you to rescale time and take sort of time adaptive time steps without breaking the symplecticity structure and all the other nice properties of it. And you can basically prove that under certain mild regularity assumptions which are satisfied, that the usual error analysis still holds. Okay, so this is some numerical results. It's like which show that these time-adaptive variational integrators compare quite favorably from an efficiency point of view to Sturmer-Villei. So, which sounds like a silly comparison, but Sturmer-Villei, because of the fact that it is explicit when applied to separable Hamiltonians, turns out to be extremely efficient, and it's actually very difficult to be more efficient than Sturmer-Villei. But it's like if you use these time adaptive methods, it's like they turn out to be slightly more efficient at least. So let me sort of skip. Sorry. Yes.
I just wanted to. I'm not sure I understand what is adaptive in the time adaptive. Is it like an adaptive step size?
Yeah. So the idea is that you have original time and you have tau, which is maybe you could think of maybe as a computational time.
Yeah, you made some change in time. I'm okay with that.
Yeah, right. And so you have this. You have a time step choice which depends on potentially your position and your momentum, right? So you choose based on the configuration of your
yeah.
solution.
So in other words, it is adaptive time steps because you're allowing the time step of the discretization to depend on where you are.
Yes, exactly. Yeah.
Yeah. Okay. I just wanted to make sure that I understood that. Yeah. Okay.
Yeah. So the point is that if you did it naively, right? If you sort of just took a symplectic integrator and you appended to it just a time step, it's like an adaptation of the time step, you would get a method which breaks basically. It would break all the geometric, well, it will break some of the geometric structure. In particular, it will break the energy conservation properties because energy is not exactly preserved by a symplectic integrator. It's only sort of approximately preserved via this backward error analysis result. And so for fixed time steps, it's like you have very good energy stability and the error sort of stays bounded for exponentially long times. But if you sort of would to naively change the time step without worrying too much about what's going on, it's like you'll find that the energy drifts. So the point is that if you were to use this Poincare transformation instead, it's like to do time adaptation, you would still have this sort of good energy behavior. So that's maybe sort of the point of distinction.
Andrew, okay, I think that something is wrong with your mic, okay, because I can't hear you.
Yeah. Okay.
You can't hear me?
No, I was saying Andrew's trying to ask a question about Andrew. You sound very distant.
Yeah, it's muffled. Okay. So anyway, let me try to wrap up. There's a bunch of stuff which I'll skip. I think to do optimization. Let me just sort of say that at a high level, the goal then is, so of course, information geometry provides this differential geometric interpretation of some machine learning algorithms. And that, of course, one of the fundamental objects in information geometry is the divergence function, and it induces a bunch of differential geometric structures. And the point, of course, is that the divergence function is related in some precise way to discrete Lagrangians. So the analogy, if you will, between information geometry and discrete mechanics hopefully will allow you to, it's like bring to bear, it's like the tools which have been developed in discrete mechanics, right, to connect, machine learning, which is typically thought of as being in discrete time, and relate it to problems which evolve in continuous time. Okay, and again, in addition, it's like you can think of various optimization algorithms as being again related to discrete mechanical systems on the space of probability distributions now. So hopefully, it's like by again leveraging this relationship between mechanics, learning, optimization, and optimal control, we'll be able to apply sort of techniques of geometric numerical integration to obtain potentially interesting new classes of algorithms. So that's basically what I wanted to say, and these are a bunch of references. So I will stop here.